Dear students, welcome to all of you. Numerical Analysis 2023 Units 4, 5 and 6 Paper CC-14 Semester 6 B.Sc Honours in Mathematics, University of Calcutta. Question paper 2023 Unit 4. So that the square root of n is equal to AB is given by square root of n equal to x by 4 plus n by s, where a is equal to a plus b. Let x equal to root n, square root of n. Then let fx equal to x square minus n is equal to 0. So f dash x equal to twice x by Newton-Raphson's method iteration formula. Xn plus 1 equal to xn minus fxn by f dash xn equal to xn minus xn square minus n whole divided by 2xn. After simplification, we get xn plus 1 equal to xn by 2 plus n by 2xn. Let xn equal to a plus b by 2. Now this a plus b equal to s by 2. So xn plus 1 equal to this xn equal to s by 2 whole divided by 2 plus n by 2xn equal to s. So this equal to s by 4 plus n by s. Hence, square root of n, actually n plus 1 is the approximation. So this is the square root of n equal to s by 4 plus n by s. Now, this is the justification note not included in your answer. And this s by 4 plus n by s equal to root n. This simplification, after simplification, we get this is the quadratic equation of s square minus 4 root n into s plus 4n. And by Giorgio formula, we can get s equal to 2 root n. So root n equal to s by 2. So root n, this n is ab, so root ab equal to s means a plus b by 2. And squaring on both sides, we get this a minus b whole square equal to 0, that is a equal to b. So x equal to square root of n, this equal to square root of n, and this equal to a plus b by 2, which when a equal to b, this is equal to a square, that is equal to a, and put a plus equal to twice a, so a, so this is equal to s by 2. So here put substitution this xn equal to a plus b by 2 here. Remember this. Next question. Question 9. Describe Newton's method for solving a system of equations fxy equal to 0, gxy equal to 0 in two variables x and y. When does the method fail? Already we have discussed this question in the question paper 2021 CC-14 Unit 4 question number 11. When does the method fail? The answer is this. The method may fail if the initial guess is not chosen sufficiently close to the root. First point is this. And second point, that Jacobian fails, not false, that is fails. F-A-I-L-S, fails to be invertible at any stage, that is J, Jacobian J not equal to 0 for any n stage. Next question, question 10a. The equation x cube minus 5x square plus 4x minus 3 equal to 0 has one root near x equal to 4, which is to be computed by the following iteration scheme. Xn equal to 3 plus k minus 4xn plus 5xn square minus xn cube whole divided by k, with the initial approximation x0 equal to 4 and k as an integer determining the value of k, that gives the fastest convergence. Let fx equal to this, so f dash is equal to this. The given iteration scheme can be written as kxn minus xn cube minus 5xn square plus 4xn minus 3 whole divided by k. So this is equal to xn minus fxn by k. This comparing one with the Newton-Raphson's iteration xn plus 1 equal to xn minus fxn by f dash xn, and we get k equal to f dash xn for the fastest convergence, that is the quadratic convergence, order 2. Now the initial approximation x equal to 0 equal to 4, so k equal to f dash 4, so this is equal to 12. Next question can be, what is the difference between the what is or are the differences between regular Falsi and secant method. And secant method, the two successive values of xi can lie on the same side of the root alpha of the equation fx equal to 0. This may lead a divergence of this method sometimes. And regular Falsi method always converges to the root alpha and is kept within the interval of containing that root. Yes. So regular Falsi always convergent, but this secant method maybe diverge. Question 2. The order of convergence for this secant method is this 1.618. Here the regular Falsi method, the order of convergence is 1. This linear convergence. Question 11. So that if the iteration function of the equation fx equal to 0 is such that a modulus of g dash x less than equal to k less than 1 for all x in the closed interval ab, the sequence xn generated by xn equal to g xn minus 1 n equal to 1 2 3 converges to the real root of fx equal to 0 uniquely for any choice of x0 initial approximation in the closed interval ab. Actually, this is the sufficient condition for the convergence by iterative method, fixed point iteration. Here we assume gx is continuously differentiable in the closed interval ab that contains the root alpha of the equation fx equal to 0, and fx equal to 0 can be rewritten as x equal to gx. And we have already discussed this question, 2021 CC-14 unit 4 question number 8, the second part of this. Next question, unit 5. What do you mean by the partial pivoting in solving a system of n linear equations in n unknowns? What are the reasons for such pivoting? Already discussed in the question paper 2021 CC-14 unit 5 question number 12a. The second part is the reason for pivoting. Each multiplier becomes numerically less than or equal to 1. The computational errors in the coefficients and the constant of the pivotal equation are not increased when the multiplied by a multiplier. Number 2, presence of large pivots guards against possible loss of significant figures during the elimination process to some extent. Next question B. Compute the total number of arithmetic operations, multiplications and divisions in Gaussian algorithm for solving n by n system of linear equations. Answer is this n cube by 3 plus n square minus n by 3. Already we have discussed this 2021 question paper CC-14 unit 5 question number 12b. Next question 13. What is the condition of convergence of Gauss-Seidel method? Is it necessary and sufficient condition? Compare this method with Gauss elimination method. The condition of convergence is the strictly diagonal dominant. This modulus value of ai greater than summation gi g equal to 1 to n, g not equal to I modulus of eig, I equal to 1 to n. And this method, this condition is called strictly diagonal dominant. The coefficient matrix is strictly diagonally dominant. This condition is known as this. And this condition is sufficient condition. That is, if the above conditions hold, then the iteration method, either Gauss-Seidel or Gauss-Jacobi, converges. But it is not a necessary condition. That means if the iteration converges, then the coefficient matrix may not be strictly diagonally dominant. Third part, Gauss elimination and Gauss-Seidel elimination. Actually, Gauss elimination method is a direct method. That is, Kramer's rule and etc. are a direct method. And here, the solution is obtained after a finite number of steps of elementary arithmetical operations. We can find the exact value, exact root, exact solution of this equation by this direct method. Whereas Gauss-Seidel method is an iterative method, that is indirect method. Actually, here we start with arbitrary initial approximation for x, and then improve this estimate by iteration, and correct this order, but convergent sequence of steps. And whereas Gauss elimination, for a large system, Gauss elimination method is not preferred. But Gauss-Seidel method, that is iterative method, for a large system, we prefer this iterative method. Next question, Unit 5, question 14. Describe the power method to calculate the numerically greatest eigenvalue of a real non-singular square matrix of order n. How do you find its numerically least eigenvalue? Already we have discussed in the question number 2022, CC-14, Unit 5, question number 15, first part, and second part is this question 15, second part. This question 15, solve the following system by Crout's method, and this is the LU decomposition method, Crout's LU decomposition method. This system, and this can be written as in the matrix form Ax equal to B, where A equal to this, X equal to this, B equal to this, and this L equal to this lower triangular matrix and U equal to this upper triangular matrix. In comparing, multiply this lower and upper triangular matrices and comparing with the elements A coefficient matrix, and after simplification we get L is this and U is this: 1 0 0, 2 minus 3 0, 3 minus 2 minus 14 by 3, and U is 1 1 1 0 1 minus 1 by 3 0 0 1. Then 1 becomes LUX equal to B, that is L into Y equal to B, where UX equal to Y. And from 2, LY equal to B gives this value of L is this matrix, and Y is say this Y1, Y2, Y3 column matrix, and B is this 3 16 minus 3. And from simplification, this we get a value of Y is this 3 minus 10 by 3, 4. And put this value of Y, this U is the upper triangular matrix and X is the unknowns X, Y, Z. And this is the multiplication and comparing this, and by back substitution we get the value of X is this: X equal to 1, Y equal to minus 2, and Z equal to 4. Next question, Unit 6. Question 16. Using 3 successive approximations of Picard's method, obtain approximate solution of the differential equation dy dx equal to x square plus y square satisfying the initial condition y0 equal to 0. This dy dx equal to fxy, for solving this linear, this first order, maybe linear, non-linear, first order differential equation dy dx equal to fxy. This fxy may be linear or non-linear function in xy with the initial condition yx equal to y0. This Picard's iteration is this y r plus 1 iteration is equal to y0 plus integration x0 to x if x comma y r iteration and dx are equal to 0 1 2 dot dot. So first approximation this y1 when r equal to 0. So y0 here, y0 is this 0 and x0 is 0, 0 to x, and this x square plus y square. So x square plus y 0 square, so 0 square, this dx x cube by 3. Second approximation, y2, when r equal to 1, this is equal to y0 plus integration x0 to x fx. y1, first approximation, this value of y1, x cube by 3, so x cube by 3 whole square, x square. After simplification, we get this is the first second approximation. Third approximation, for r equal to 2, we get y3 equal to y0 plus integration x0 to x fx y2 dx. This y2 from the previous iteration, this x3 by 3 plus x to the power 7 by 63 whole square, and after simplification we get this the value of y for the third approximation. Question 17. Using Euler's modified method, solve the following differential equation dy dx equal to x square plus y with y0 equal to 1 for x equal to 0.02 by taking step length is equal to 0.01. Now for solving the first order differential equation dy dx fxy with the initial condition yx equal to y0, the initial approximation of yi plus 1 is given by yi plus 1 0 for initial approximation. This is equal to yi plus h into f of xi yi, I equal to 0 1 to n minus 1, and this is actually Euler method. So the initial approximation of yi plus 1 by this Euler method, by the Euler's method, we get this value. And after that, for the r plus 1 at the approximation of yi plus 1, we use modified Euler's method. This yi plus 1 r plus 1 is equal to yi plus h by 2 and bracket f of xi yi plus f bracket xi plus 1 comma yi plus 1 r at the approximation, r equal to 0 1 2 and so on dot dot, and I equal to 0 1 to n minus 1. So here dy dx equal to x square plus y equal to fxy, say with the initial condition y0 equal to 1, so x0 equal to 0 and y0 equal to 1, and step length is 0.01, so x1 equal to x0 plus h, so x0 is 0 and h is 0.01, so this x1 equal to this, x2 equal to x1 plus h, so 0.02. And compute y1, that is I equal to, for I equal to 0, this y1 0 by the Euler's method, y0 plus h into f of x0 y0. Here x0 is 0 and y0 is 1, so 0 square plus 1, this h equal to 0.1, so this is 1.01. And this r equal to 0, for r equal to 0, in this method r equal to 0, so we get y1 1, y1 for the first approximation 1. Formula modified Euler's method, y0 plus h by 2 f of x0 y0 plus f of x1 y1 0, previous value 1.0 is. Because simplification, we get this 1.0100505. And second approximation for y1, and this is the value y is equal to 1.010050753. So y1, that is the y at the point 0.0001 at the point x1, value of x1 is equal to 1.01005, corrected to 5 decimal places. Next, compute y2. So initial approximation by Euler's method, y2 0 equal to y1 plus h into x1 y1, value of this initial approximation. Next, first approximation of y2 by modified Euler's method, this y1 plus h by 2 equal to this, so this value of this 1.0201782555. Second approximation for y2, this y1 plus h by 2 bracket fx1 y1 plus fx2 y2 1, the previous value of this. Simplification, we get 1.02020364. So y2, that is the y at the point 0.02 is equal to 1.02020, correct up to 5 decimal places. Thank you for watching this video.